Um, so I realized too late that I had a really lousy title for my talk. It should have been something cool like, so Mr. Smith, you want to open a bank account? Like that's really what this talk is about. But the underlying issue, or the technical name is fuzzy entity matching. So we got the obligatory, why am I up here talking? Why should you listen to me? So I've got a boutique big data consulting company. Boutique sounds way better than small. There's just 5 of us. But we help clients with issues around big data problems. So Hadoop workflows that we implement using cascading, which is an open source API. We do stuff with Cassandra, with Solr, like on the search side, machine learning, et cetera. So we do consulting on that, and we also do training. So actually, I created the training materials for DataStax for their DSE Solr search, and occasionally I teach that class for them. I also teach classes on Hadoop and machine learning and other things like that. I enjoy teaching so much that I volunteer teach high school programming classes, which if you've dealt with high school students, like, it means I really like teaching. All right, so when I go to talks, I really enjoy having a concrete use case, like as the context. So as the person's talking about things, I can get a sense of what they're trying to tell me and why it matters. So in this case, we're going to start with the problem. Let's say I'm going to a bank and I want to open an account. So in this case, this guy who's sitting across the table from me, he's pleasantly chatting with me, but what's really going on in his head is, should I open an account for you? Like, would that be a big mistake? You know what, would I regret doing that? Right? So it's about calculating the applicant's risk, trying to figure out, like, should I do this? Should I open the account for them? So what's happened is I've provided, me as the applicant, a bunch of information. My name, date of birth, maybe social security number, details like that. And what they need to do is be able to look at my account history. They want to be able to find every single account that I've owned or had control over or been associated with, whether there were problems with that account. That's a key part of this. Right? So really it's about matching up who I say I am, the details I've provided, with everybody that they know something about. Right? Does that make sense? So that's the fundamental problem here. So matching people. I've provided some information, or in the case of the banker, I've got information that the applicant's provided. And what I need to do is match it against all the data, not just the data I've got. Right? That's a fundamental problem, because if I've been a total bad boy over at Wells Fargo, you know, I've been bouncing checks left and right, and then I go over to Bank of America and I say, oh, I'd like to open an account. If they don't know what's going on at Wells Fargo, they don't know that I'm somebody they shouldn't open that account for. Right? So fundamental problem, they have to have data on all the bank account activity, but like there's no way in hell Wells Fargo is going to give Bank of America their customer list and their account status, right? And vice versa. That's just not going to happen. These are competitors. So what do you do? Well, the solution to this problem is a company called Early Warning Services. They provide, it's a joint venture, so they provide this common place for the banks to send their data to where they know it's not going to get passed around to each other, right? It's the trusted third party. So joint venture, the biggest 5 US banks, plus then like 800 plus other financial institutions send them information. So they have data on pretty much everybody in the US who has a bank account. Right? So that's the key. They've got the data. But now the problem is you've got that data. How do you solve that person matching problem? Right? And by solving it, I mean you get good results and you get the results fast enough. Right? So it's both quality and the performance on that. And now we get into the issue of fuzzy matching. Right? So in general, what do I mean by fuzzy matching? If I've got something that I'm looking for, like this blue triangle over here, I want to get everything that I think is equivalent and nothing that's different. Right? That's my goal. Now in this case right here, you know, key point is how do I define what is similar or what is dissimilar? So in this first row here, what I've defined arbitrarily is I'm saying rotation doesn't matter. Right? The triangle is rotated, it's still the same triangle. I've said that if the color is close, right, it doesn't matter. So here it's a slightly darker blue for that second triangle up there, this guy right here. And I'm saying, okay, that's equivalent, that doesn't matter. And I'm saying if it's slightly smaller. Now, notice that I'm using terms like slightly. So right away you get into this problem where it's not a step function. It's not like down here where I say, okay, if it's a circle versus a triangle, forget it, it's not the same. It's this slope I've created a gradient that says, well, if you're pretty close to the color, you're okay, but if you're too far away from the color, then you're not okay. Right? So we get into this area of gray that we'll talk about. And we've decided things like, a structural change like this to the triangle is significant or not. So we're arbitrarily coming up with aspects of attributes that we decide are important and that matter and that have to match, or that have to match close enough, or that, if they don't match, we're done. So why is it hard? Well, as we've talked about, there's fuzzy areas. Like in this case right here, what if it's a really light blue color? Is that a match? I don't know. Or what if we've got some attribute like a really thick border around it? Would I consider those two things equivalent? Or what if the triangle is really small compared to the other one? Right? So again, we've got these slopes, and you have to, the problem is when you decide if it goes past this level, then it's not the same. You're creating a step function, essentially. And then if somebody's just a little bit past that edge and they fall off it, and so now it's not similar, you've removed them from your list, right? Which is a problem. So that's one problem, lots of areas of gray. The second problem is you can't use Cassandra. Right? The fundamental problem is that Cassandra is great. If I've got a row key, then wow, it's super fast for me to look up that row key, and if I look for that row key and it's not there, then I know I don't have it. Right? So fast and accurate. But I don't have a row key. It's a fuzzy matching problem. So fundamentally, I can't apply the key feature of Cassandra to the problem. And the third thing is computationally intensive. So imagine I'm comparing two things, and I've got like, I don't know, 100 attributes, like strings. And I'm doing string edit distance, right, to do the comparison between. Okay, that's a computationally intensive problem. Right? That can chew some serious CPU cycles. All right, so we've been talking about triangles. Now let's go to people. So in this case right here, these are all pictures of people who are speakers at the Cassandra Summit here. And there's me over there, a really bad headshot that somebody did a couple years ago. I'm getting a new one on Saturday. So I've got information on all these people. And now I'm being asked about a specific person, right? I'm being asked about me, like, am I in this group over here? And the thing is, I want to quickly find all the good matches. One of the challenges here is, it's not like I can search until I find a good match. Right? I need to find all the good matches, which means I've got to go through everybody. Right? There aren't any real shortcuts here, or so it appears. Now, a point I'm going to make here is we're not doing batch matching. So a lot of people, when you talk about fuzzy like matching, they're thinking about batch, which means it could be a self-join. Like I've got this long list of people and I want to dedupe. Like I've got entries in here that are close, I've got to deduplicate them. Or let's say I've got a list of people, I get data from another source and I need to merge those together. But again, there's going to be a bunch of duplicates in there, or near duplicates. How do I do that merge? I gave a talk a couple months ago at Hadoop Summit about doing that kind of batch fuzzy matching at scale. Different kind of problem. This right here we're talking about, it's ad hoc. I've got this one person or thing, and I'm trying to see what in my large corpus or set of data I've got that's similar enough to be considered a match. So, what's a good match? Right? So what we're doing here for people is we've got attributes, basically fields with values for people. And in this case, we've got name, address, city, state, zip. Right? So are these two people the same? Right? If you looked at this right here, would you say these two are the same? Everybody says yes, because as a person, you look at it and you know, oh, zip code matches, the +4 part is like a subspecifier or whatever, it's okay. And Bob and Robert, those are sort of equivalents, those are synonyms. Right? So you would look at that and you'd say, yep, those are exact matches. What about now? Like most people look at it and go, yeah, probably, but yeah, there's some issues here. For example, I mean, the fact that this one doesn't have a zip code, this one does, you look at that and you go, whatever, okay. Washington versus WA, that's an alias. The fact that there's no middle initial here is okay. Like sometimes you don't get the middle initial. Not having an apartment number, okay, sometimes you get the apartment number, sometimes you don't. But the fact that it's 3220 versus 220 there, is that a typo when people are entering? And it's amazing how noisy data is. Like in your mind, or at least in my mind, when you think about bank data, you're like, this is, wow, it's going to be like spot on. No. So you get typos, weirdly enough, because you got humans involved entering data that people scratch onto forms in illegible ink. So you get typos. So you look at these two things and you're like, well, it wouldn't be 100%, but you'd say, yeah, probably. So 2 things then. One is normalization. So being able to know that Washington and WA are the same thing, they're different strings to a computer. Knowing that they're the same thing, that's an issue of normalization. Right? Similarly with like Bob versus Robert, you could treat that as a normalization problem. And the second thing, though, is how do you know what features to focus on? What's important when it's the same or when it's different? So a typical approach here is for calculating similarity, and there's many, many ways to do this. There's, I think, God knows how many research papers or PhDs have been done on similarity. But this is a common approach for record similarity, where you say, for each field, I can calculate a degree of similarity between them. And often how you calculate that winds up being field specific. Like zip code, if the primary part matches, we're pretty close to being 1.0. If the subpart doesn't match, it's not so significant. And then for each field, you give it a weight. How significant is it if it matches or doesn't match? Right? Like zip code. Zip code matching is more significant than state matching, because zip code's more specific than state, so it has a higher weight. So then what you can do is if you give each field a weight, and the sum of those weights equals 1, right? They sum to 1.0. So each field has a weight from 0 to 1, and if you sum all the weights of all the fields, they're going to sum to 1.0. Then for each field, you can take its similarity value times its weight, and you sum those, and you're going to come up with a number between 0, which means these things are completely different, and 1.0, they're an exact duplicate. Right? They're an exact match. So that's a simple way of calculating a similarity score from 1 to 0, from 0 to 1, and that's what I call a match similarity. But I asked the question, does it scale? The answer is no. Right? The issue is, again, for a single person like me being matched against hundreds of millions of potential people, you have to do that comparison for every single record. Right? And we talked about it being computationally intensive. Right? It works for a couple hundred, maybe even a couple thousand people. It does not scale to hundreds of millions. Right? So fundamentally, what you need to do here is figure out a way to do fewer comparisons. How do you do fewer comparisons? All right. And that's where search comes in. Right, so search. Who here has experience with search in general? Hands up. Anyone? Quite a few people. How about specifically Solr? A couple people. All right, great. Is anybody using DSE with Solr? Fewer still. Okay. All right. If I accidentally say Solr in here, just because I'll do that. It's an open source project that provides search. We'll go into it in more detail in a little bit. But what I'm going to talk about here is in general search. So search is fast similarity. Right? Search is all about, it takes a query, like I'm looking for scale unlimited blog. Let's say that's my query, 3 words. It actually turns that into a document, just like any other document that I've got on my search index. It turns it into a document where a document is essentially a feature vector. It's a multidimensional vector where there's one dimension for each unique word. Right? So if my search was scale unlimited blog, I'd wind up with a feature vector that has 3 dimensions to it. So it's a 3-dimensional feature vector. And the magnitude of each weight is based upon something called TF-IDF. So term frequency, inverse document frequency. Really what it means is how often does this word occur in this document? That's the term frequency part. Like how significant is the word in the document? And IDF is inverse document frequency. It's like how significant is this word across all documents? As an example there, the word the is not very significant because it's in every single document. So the fact that my query has the word the in it doesn't matter. So its document frequency is really high. It's like 1. Inverse document frequency then becomes very low. So it's sort of how significant is a word across my entire corpus. Basically, you get a weight for each word in this feature vector. And that actually gives you a vector then, because each dimension has to have a magnitude. Right? So that basically gives me this 3-dimensional vector here. In this case, for the 3-word case, it's 3 dimensions. So I've got 3 values. And each value has a weight or magnitude set according to term frequency times inverse document frequency. Think of it as this, though. Here's this term vector that I've got for this document. I can compare it to some other document's term vector, and it has an angle between them. Right? Vectors have angles between them. If that angle is 0, which means these two term vectors are exactly the same or have exactly the same sort of direction, then the angle 0, cosine of that is 1. So great, they're exactly the same. Cosine similarity gives me 1.0 if they're exactly the same. If they're 90 degrees opposite, cosine will give me 0. There's nothing in common between them. And if they're opposite each other, so the angle is 180 degrees, it's minus 1. It's actually showing negative correlation right between it. So that's a search similarity score. It's a common one. There's other ways to do similarity scores, but this is the basic one inside of Lucene and that Solr is built on top of. The key thing is it's super fast for search systems to use this to find the best documents. However, this cosine similarity or search similarity, it's not the same as the match similarity that we were talking about earlier. Obviously, right? Match similarity had per field weights and maybe edit distances and all kinds of crazy stuff. Generally it doesn't have the same level of sophistication because it's really trying to be fast. So how do you deal with that if you're trying to use search to narrow down the set of candidates that you then have to do match similarity with? Right? Because that's the key point. If I can use search to say, out of the hundreds of millions of people that I know about, what are the 100 that are likely to be similar, to be good candidates? And if I have it 100, then I can do that match similarity, and it's OK. Right? So I'm using search to narrow down the candidate set. Right? But the issue here, as we said, is search similarity. That candidate set I get isn't going to be exactly the same as match similarity, the score. So what do? Well, you throw a bigger net. Right? If I say, like, at most I'm going to get 10 matches, I expect that I'm only going to get at most 10 matches, or maybe 10 matches is all I care about. If I get more than that, I'm dealing with somebody who's creating a whole bunch of bogus IDs, and I don't want them anyway. But let's say I get at most 10 matches. Well, then I could say, OK, let's find 100 candidates, or maybe 1,000 candidates. Like I scale up that 10 by some amount. And that's my candidate list that I then do match similarity on. Right? Does that make sense? So basically, using that super fast search to narrow down the set of candidates to the level where I can actually do this match similarity on what's left. All right, so it's a two-step process. We've got, like, here's the information being provided by some person. They got a name, social security number, and maybe a date of birth, right? Maybe they'll have address as well, but let's say we got these 3 attributes for them. So I'm going to turn it into a query, and one of the interesting things you can do with Solr and other systems is you can add weights to the fields, right? You can put weights in there that are similar to the weights you put on fields when you're doing that match similarity. Which fields matter more? So in this case right here, I'm saying if the social security number matches, let's boost the importance of that by 10. If the date of birth matches, let's boost it by 5. If the name matches, let's boost it by 3. So essentially I can provide some hints to search where I'm using weights for fields that are similar to the weights I use when I'm doing matching. Okay? So your search system then goes out and hits the index, and it comes back with its list of what it thinks the top candidates are. And I say, give me 10, give me 100, whatever. And it'll come back with these ordered. That's the first step. And then the second step is I run the matching logic against those results. And the matching logic is going to come up with different numbers based on its way of comparing things. So it's essentially re-ranking things. Right? It reorders things. And then it can say, well, I know anything less than give some number, 0.7. I don't consider that a match. Right? So I'm going to get left with some subset of these things. Make sense? So two-step, search, then re-rank using the match similarity. One of the things I should have said at the beginning of this talk is that there are some details about the implementation for early warning that I obviously can't talk about. Like I'm not going to say, oh, if you put an umlaut over a vowel in your name, we can't match the name at all. That actually isn't a problem, so don't bother trying that. But obviously I can't go into the details of exactly how their match logic works. I gave you a very simple approach. They've got way more sophisticated things, but you get the basic idea here, right? So how do you pick n, that scaling factor, right? I'm looking for 10, up to 10 matches. Let's search for 100. How do you pick n? Well, you can make n small if your search similarity results are very close to your match similarity results. The closer those two things are, the smaller n can be. Right? The smaller your net has to be. And you can make those things closer by doing things like ensuring that your data is normalized before it goes into Solr. So for example, that the zip code thing. Remember the zip code thing? There's a zip and a zip plus 4, right? You can take it and say, let's break it into a zip field and a zip plus 4 field, and we'll search on just the zip or zip plus 4 if we've got it with a higher weight. And that way, if the person only gives you your zip and you have zip plus 4, it still works versus not finding it at all. If it didn't find it at all, that means your search similarity is being skewed relative to your match similarity. So the more normalization you can do, the better your search results can correlate with your match results. Now, why do you care about n? Well, if n's too big, it's like this case right here where I'm throwing this big red net, and the stuff in purple is the stuff I actually care about. So if n's too big, we got a performance issue, potentially, because we're putting more load on the search system to give us back these bigger set of results. And then that bigger set of results, I still have to go through and do that matching logic against each one. So you get hit twice. Now, what happens if n's too small? Well, if you make the n too small, you might get this case where you're actually missing some matches you want, because that circle isn't directly aligned with the match circle. And so if it's too small, you get some false negatives, which, depending on your use case, may be OK, or it may be really bad. Like this right here might be the one account where the person that's trying to open an account, the one sort of identity where the person who's trying to open the account was bouncing checks like they were a Harlem Globetrotter, you know, dribbling a basketball. And you don't know about it, and so you're like, oh, sure, let's open an account for this person. Right? So how much you care depends on your use case. And the key here is, right, the tuning the search to mimic the match similarity. Right? So as we talked about before, you can do things like weight the value of matching different fields when you make your search query. That's a common technique for getting these more in alignment. And the normalization. So, as I said, I mentioned Solr, and I would talk about it. So Solr is an open source project out of the Apache Software Foundation. It's built on top of Lucene, which is a low-level information retrieval engine. The key things about Solr are that and Lucene is that it's highly scalable, like up to billions of documents, and pretty darn fast even at that level. And you can customize it and configure it to your heart's content. So often you can make Solr do your bidding. You can make Solr do what you need it to do as far as the search stuff. And then the third key point is that it's integrated with Cassandra as part of the DataStax Enterprise Edition. We're going to talk about what that integration means in a little bit. But basically, there's some nice goodness about that integration. What you do in Solr is you have a schema. Lucene itself is it's almost like Cassandra in a way, in that you can have these documents, and every document can have different fields in it. And you can put anything in there that you want. Like it's schema-less. Solr puts a schema on top of that. So you have fields, and you say what type they are. And by saying the type of each field, you say how it gets analyzed and how it gets searched. Right? So this is the schema that you're putting on top of the data that's going into the index. So for example, I can have a name field there of type text, and I can define the text field type to say, if you see Robert, treat it as Bob. Right? I can do things like that. I can do synonyms. I can control how it gets tokenized, how it gets broken up into individual words. So DSE search with Solr. So what is it? It's not part of the open source Cassandra project. Right? It's an extension that is specific to the commercial product you get from DataStax. What it does is it lets you say, for this table in Cassandra, I'm going to have a Solr index that is automatically kept in sync with it. So if I write to Cassandra, my index gets updated. If I delete from Cassandra, my index gets updated. And likewise, since my Cassandra data is replicated and distributed across multiple servers, my Solr index is replicated and distributed across multiple servers. Right? It leverages all that underlying goodness from Cassandra. Okay? So essentially, the Solr support in DSE kind of competes with Solr Cloud, which is the Solr open source project's extension to do more of this kind of cloud-based distributed search, and also Elasticsearch. Now, as I mentioned, great, it's leveraging the existing Cassandra replication, so you get like reliability. A node goes down, you can still search because you got copies of the data on other nodes, just like with Cassandra, right? Node going down isn't a problem. And the data is distributed, so if I need more capacity, I can just scale up my cluster, and I got more search capacity. And you get like replication between data centers, which for enterprise solutions with solar is a beautiful thing. I can have a data center, East Coast, data center, West Coast. I write to one, network topology replicates over to the other. It's a beautiful thing. Just to dive in a little bit, like often people are like, well, how exactly does that solar indexing thing work? In Cassandra, there's something called a secondary index, right, that you can use. Well, there's a hook there, a handy-dandy hook that's effectively undocumented, but it's there. Strangely added by a DataStax engineer that lets them hook into it and do this thing where as documents, as rows get modified or added to Cassandra, the hook is in there and it says, oh, okay, I'm going to queue up something. I'm going to queue up a solar index change for every Cassandra row change. Right? So that's how it keeps it in sync. But a key point is it's way slower than the Cassandra writes. Like a Cassandra write, it's whatever, pick a number, 20,000 writes per second per node, on a regular hardware. Pick some number. Okay, solar is nowhere close to that for a couple reasons. One is solar, when it writes, it does analysis on the data. Like it's sitting there tokenizing it and normalizing it and doing all this work versus a Cassandra write is just, okay, here's some data in the mem table. Oh, here's some more data in the mem table. Right? Solar has to actually do work. The other problem is solar, when you write a document, like a row in solar, you need to have all the data to write that row. So what that means is when you do a solar update, when you update in Cassandra, like a single field, a single column in your Cassandra row, what it has to do behind the scenes is it has to read that row. It has to get the whole row so it can build that solar document to write it. So it's violating the never read issue, right? When you're writing, it has to always read before it writes to build the full solar document. So how much slower it is, I don't know. I use something like 10x as a rule of thumb. But I think it varies a lot on your configuration, how much work solar is doing, et cetera. So how fast is it? Oh, yes, question. Trigger invoked exactly once per write. So the secondary indexing hook will get called exactly once for each row mutation.
Regardless of how many Cassandra nodes are actually writing
Well, the secondary index, so the interesting thing is the secondary indexing hook, it's not at the level where you're writing to some Cassandra node and then that gets distributed out to other nodes. It's actually on the individual node. So you're going to wind up doing this indexing process 3 times if you have 3 copies of the data. Right? It's actually happening on the node.
Does it happen at mem table flush?
It's an interesting question. In general, yes, it happens. Well, that would be a good way to think about it. Yes. Yes. It's the more I dug into this when I was writing the documentation, the more complicated it gets, of course. So it was like peeling an onion. So when a record gets flushed by TTL, you essentially have a row mutation, and then the regular process happens. Yes. It will replicate into the solar index, yes. You'll get the effects. So the goal of the whole system is, if you have this in Cassandra table, if like you make a request to Cassandra and you get this, then you get the same thing on the solar side, keeping those things in sync. So if TTL triggers and and you've got some data getting deleted, it will get deleted from solar. So this hook. Correct. It's a hook at the. If you do a delete using CQLSH, right, you get rid of a row, then automatically solar will be updated. Yes. So the solar index is also saved on the same Cassandra nodes. The index isn't saved in a Cassandra table. The index is saved to the disk, the local drive. Yeah. But what's interesting is they do leverage the Cassandra tables for other things, like that solar schema that I was talking about with the fields and the types. That essentially is stored in a Cassandra table, and that's how they replicate it out to all the nodes. So they leverage that a lot. So the question is, how do you associate a column, with specific Solr stuff? And so that Solr schema that I showed you there, what happens is it associates the field names in there with the column names in Cassandra, right? So if I want to do a certain thing with the text in Solr, I just create a field in Solr that does whatever I want it to do, and I make sure the name of that field matches the Cassandra column name. All right, so I'm gonna keep going. We can definitely talk afterwards if you have more questions. So here's some performance, like using mock data. We wrote 170 million records. This is into a 8-node cluster. The writing took 2.5 hours. So definitely much slower than if we were just slamming records into Cassandra without Solr. When the writing to Cassandra finished, we were about 15% of the way done with indexing it, right? So the indexing is running behind. And when the indexing runs behind, it also slows down your Cassandra writes. There's actually this back pressure support that tries to prevent you from overloading the system, so it'll slow down your writes, which is why the writes took longer than they would normally. And then after the Cassandra writes finished, it actually took about another 12 hours for the index to be totally in sync. Now there's definitely things you can do to reduce that amount of time. For example, you can offload work from Solr into whatever is generating the data you're putting into Cassandra. So for example, you can take the Solr analyzer chain, that code, and plug it in upstream so that you're already tokenizing the data, and then you can use a really simple white space tokenizer in your Solr scheme. So you're essentially shifting CPU load away from Solr into, in our case, a Hadoop workflow. Okay. All right. So the system overview. So I mentioned we have a Hadoop workflow. So basically the way this system works is, we get all this raw data coming in from the banks, parse it, validate it, normalize it, and that's all happening through a Hadoop workflow. Right? Then after it does that, and this workflow, we build our workflows using something called cascading, which is kind of a Java API on top of Hadoop, so you can stay sane when you're working with things like joins and whatnot. And then after it's done that, there's this thing of getting it into Cassandra. And we still use Hadoop for that. We actually, in Hadoop, there's map and reduce tasks, 2 phases to map reduce. And in reduce, you can control the level of parallelism. You can say, I want to run 3 reduce tasks in parallel. I want to run 1 in parallel. I want to run 100 in parallel. So we actually, in the reduce task, is where we talk to Cassandra because we have better control over the amount of parallelism, like how hard we're hitting our Cassandra cluster. It's kind of interesting because the actual Java driver for Cassandra also lets you have some level of parallelism in it. So there's sort of this, where's the right place to do it? And as I mentioned, the bottleneck, though, is the Solr indexing. There is an approach that we tried, which is kind of interesting. You can write in the Cassandra table where the Cassandra table isn't hooked up to Solr. Right? You just have a regular Cassandra table, you write into it, it's super fast. And then after you do that, you say, oh, now we want to associate this Solr index with the Cassandra table. And it starts doing the indexing in the background. Turns out that's currently single-threaded, so it took I don't know, after about 18 hours, we killed it. So it was slower. I mean, the cluster resource got released faster, the Hadoop cluster, but the overall time was significantly longer to get a full index in there. All right, so we got this Hadoop cluster, writing things into this Cassandra plus Solr guy, and then we've got this actual API that's making Solr queries against it. Does that make sense? So ingest performance. We talked about how you want to do writes without reads. Right? That's the fundamental thing. But the problem here is if you're adding an entry, what we tried first is, well, we got to see if we already have this entry in there. So we do a Solr query, and if we got the entry, then we just add the data to it. Otherwise, we would create a new entry. But that's really slow. Now we're doing a query before every write, which is really bad. So the key, and I'm just going to quickly mention it here, is we set the row key in Cassandra to be a hash of all the searchable fields. So what that means is if all the searchable fields are the same, the hash is going to be the same. We know we got that same entry in there. Otherwise, it's going to be different. And so what we wind up doing is, the address changed. We'll get a different entry in there. But we just expand our net a little bit more to handle those duplicates. And then our ingest performance is way better. So make sense? Right? So for each Cassandra row, you got to have a unique row key. And normally we were setting that row key to a UUID, right? But instead what we do is set the row key to the hash of all the fields in the record that we search on. Right? And so if those searchable fields are the same, we're going to get the same hash. So if we try and add essentially the same entry but with different like account data, which we don't search on, then we'll say, oh, we already have this one in there, and we can just update the account data. If, on the other hand, any of those fields have changed, their date of birth, et cetera, then we get a different hash, we'll get a different row. All right. So summary. This is for ad hoc, kind of deduping, fuzzy matching, not batch level. See, I think my slides from Hadoop Summit are posted on somewhere if you care about similarity at scale, like doing the batch level dedupe. The key is we use search to get a small set of candidates that we then do that expensive match similarity against. The pain, like with all this stuff, it's always the data prep is where the pain is. Like the normalization, cleaning up the data, dealing with messy data, that's the problem. And using essentially Cassandra plus Solr in DSC, that makes this actually pretty darn easy architecturally to handle. Right? We just treat it like a Cassandra write on the left side where the Hadoop stuff's flowing into Cassandra, and on the right side we treat it like a Solr index, and we don't care about exactly how that magic happens in the middle.